So welcome everybody. It's a great pleasure to see so many of you being interested in our today's topic on computational astrophysics. It's a particular pleasure for me to introduce our speaker, Romain Teyssier, who many of you probably know from his work in computational astrophysics as one of the developer of the Ramses code, one of the leading numerical codes for different applications in astrophysics. So we will hear about galaxy formation at cosmic dawn today, but this code is, of course, as many of you know, also used for many other use cases in computational astrophysics. So Romain studied in Paris and also got his degree there. Then he went to Lawrence Livermore National Laboratory and then returned to France to CAA in Saclay. In 2013, he moved to Zurich on a professorship at the University of Zurich. And rather recently, in 2021, he moved over to the United States and started a professorship at Princeton University, where he's been since then now. Of course, Romain has received a couple of awards and prizes. There are, for instance, the Grand Prix Scientifique, Simon et what's that? Sino de Ducat. Right. So okay, my French is not that good. And he has also been involved in Euclid and won the Euclid Star Prize there. All right. So with that, I would ask Romain to start his talk and tell us about a numerical perspective on the cosmic dawn.
All right. So pragmatic approach here means that we observe galaxies with a given star formation rate per unit surface, because we observe them as disks, versus the gas surface density. And that's the data point. And so we can actually calibrate the efficiency up and down until our simulation match observations. Pragmatic approach, where this parameter is unknown. The problem is that those galaxies are local spirals, like the Milky Way. We have also a few local starbursts, and you see that there is a factor of 10 difference here. And so now if you want to also model galaxies at cosmic dawn, like in the regime where James Webb discovers them, what value do we choose? Because we cannot calibrate on these because we don't know them, right? So that's kind of the previous state of affair here, that this pragmatic kind of approach has a problem, and it's not predictive. You cannot predict the star formation using this. So then what we do, so that's the first ingredient, right? Star formation. The second ingredient is supernova explosions. So we need supernova explosions to release energy. We think it's 10 to the 51 erg per supernovae back into the gas. And this is used to regulate star formation. It's a very, very important ingredient in galaxy formation. And the problem, again, is that those supernovae explosions are very tiny. And I'm only talking about the supernova remnant, this large sphere of hot gas in the ISM, which is a few parsec in size. Again, completely unresolved by our galaxy formation simulation. So how do you deal with this? Well, you have to use, again, a subgrid model, which basically encode the star formation, the supernovae process into two simplified phases, an energy conserving phase followed by a momentum conserving phase, where we basically dump either energy or momentum into the interstellar medium. Right? Can you hear me? Great. So this model again is, the best we can do. given that we don't resolve the actual size of the blast wave, to inject back energy into our simulation. So those are the two main ingredients in galaxy formation: star formation with a recipe which is, calibrated, and supernova feedback with this kind of approach, momentum injection if you don't resolve the supernova blast wave. All right, so can we go beyond that? And that's kind of the thing that many people are working on, which is to, it's fine. So it's good to have
There's some other problem with this thing, so we'll have to go like that.
Okay.
Yeah.
Okay, so now when we go back to our star formation colleagues, they tell us star formation is more complex than just a Schmidt law. And actually there is hope maybe to go beyond a more predictive model. The key point is that star forms inside a turbulent cloud. So that's a nearby turbulent cloud, 30 radius, and the image is 100 parsec across. Again, that's close to the size of one of our simulation cell, right? And inside the simulation cell, we have this turbulent medium, and star formation simulation like this one do form star using various techniques that I'm not going to dwell on today inside this turbulent medium, and they predict that the efficiency per free fall time, the same parameter I described, can be actually computed from first principle as a function of the turbulence and the density inside the medium. And so now we have a model which is called the turbulent or gravo-turbulent model. That is actually the result of many decades of research by people like Ralph Claessen here, for example, that computes the epsilon FF parameter as a function of two main parameters: the free fall time, the local free fall time of the cloud, and the turbulence crossing time or the dynamical time inside the cloud. So if you know the turbulence in the cloud, you know the density in the cloud, you can predict epsilon FF from first principle. And so do we find the right value for local galaxies? Yes, we do, because for the Milky Way, for example, the properties of the turbulence and the gas density gives you an efficiency of a few %, which is here. And maybe in high redshift galaxies, and actually that's what we find, the turbulence and the density are such that the efficiency is moving up more towards 10%. And so we can predict the efficiency of star formation using these models. So I have more details in the next slide. The key parameter that we need is the turbulence kinetic energy. And so for this, we use an approach called large eddy simulation approach, which tries to model as a passive scalar the evolution of the kinetic energy of turbulence, which is this quantity kT here. And this equation is a new equation which describes the time evolution in space and time of this quantity. And so this is used a lot in engineering to predict the level of turbulence in unresolved scales inside our cells. This is actually used also in type 1a supernovae to model the flame dynamics. And this large eddy simulation is a very powerful tool, but there is a catch, of course, that this equation here, there are terms, that's the creation of turbulence here, and the dissipation of turbulence. And of course, we don't know those terms. The only way you can know those terms is to actually do the simulation at small scales, right? So we need to rely on a model. We have a model to create and dissipate turbulence, and this is usually referred to as the mixing length model, which is based on a source term based on the shear tensor and a dissipation term based on the mixing length timescale. So this model, some people argue it's not very accurate, and I will give you that, but it gives you an estimate, rough estimate of the turbulence inside the cell. And so again, I want you to have in mind that one computational cell for us is the entire cube here. And this sigma t variable is basically the turbulent energy inside this box. And then what we do is, using this quantity, the turbulent energy inside the box, we extrapolate down to very, very small scales, all the way down to star-forming scales, to compute this epsilon FF parameter. And so that's the last ingredient. So that's the star formation model we have. Same thing, Schmidt law, except now epsilon FF is computed from first principle using this turbulent cascade all the way down to star forming scales. And this model was actually invented by Christophe Federat and Ralph Klessen, and there are variations of it. And that's the model we use. So the good thing here is that suddenly your star formation recipe becomes predictive. Right? Of course, you can argue that the model is not accurate. So the prediction is not accurate, maybe, but that's the model we have. And so we can invalidate the model and maybe design a better one, right? And that's where we are. And there is actually a free parameter. Let me go back. The mixing length. The mixing length is a free parameter, and usually we use the grid size, the resolution of the grid, as the mixing length, but you can use twice the grid size, half the grid size. It will change the result a little bit. Okay. All right. Okay, so now let's dive into the modeling of cosmic dawn. So equipped with these tools, right? So predictive gravoturbulent star formation recipe on one hand, and supernovae explosions modeled by energy conserving / momentum conserving phases. So what kind of observable do we have about cosmic dawn? There are mostly two pre-James Webb observables, which is this Thomson optical depth, which is measured by CMB experiments. So basically what you do is you look at the CMB sky with little, this little patch of microwave radiation on the sky. And depending on the thickness of the ionized layer of hydrogen between the CMB and us, we can estimate how thick is this layer of ionized hydrogen. And that's what Planck measures. And so in your galaxy formation simulation, you're going to form star, you're going to reionize the universe. So, and then you're going to obtain a certain layer of neutral hydrogen and ionized hydrogen between us and the CMB. And these are different models for this optical depth. And so the key point is, using Planck, you need to reproduce this optical depth in order to validate the galaxy formation scenario you have at cosmic dawn. The second pre-James Webb probe that we have is a quasar absorption line. So each of those points is a different quasar, which actually is deep at very high redshift, and the light basically travel between the quasar redshift and us, and we can measure the H1 fraction, or 1 minus the H2 fraction, between us and this quasar using absorption lines. And those points give you the fraction of H1. So it's 1 at very high redshift. The universe is neutral. And then the universe is progressively ionized. You have less and less H1 until it's fully ionized at redshift 6. And then you have no more H1 or very little H1 left. Okay? And so basically those two measurements tell the same story, right? That's how much H1 you have between us and the high redshift universe. And you see the same model here going through the data points and kind of converging to a picture, which is that the ionization is complete at redshift 6 and starts at redshift 10 and progressively ionize the universe. Okay, so now the goal of these simulations is to reproduce these results. So to do that, there is the last ingredient, which is we need to model the radiation. And so that's actually the most challenging part of the story. You need to model the transport of photons, of ionizing photons, which are emitted deep inside galaxies, escaping the galaxies, if they're lucky. And then they travel outside of the galaxy, ionizing a bubble around the galaxy. And if you have enough of those photons, all the bubbles will collapse, will merge, and the universe will be fully ionized. So in order to describe this, we need to use the radiative transfer equation, which is at the top, which is a very complex equation because it's 6-dimensional. You have 3 dimensions of space, 2 of angles, direction, and 1 of frequency. In practice, especially if you do this with millions and millions of sources, which are the star in your simulations, right? It's too expensive. So what we do is we average over the angles. We take angular moments, and we end up with 2 equations, energy conservation and flux conservation. Except that the second equation depends on this guy here, which is the Eddington tensor, and we don't know what it is. So the same thing that for turbulence, we don't know what the terms on the right-hand side were. We don't know what the Eddington tensor is. I mean, it depends on the angular distribution of radiation, but we don't know it because we average over it. So you need a closure relation. You need to have a way to close this relation. And the way we do it is to use the simplest model available out there, which is the M1 model, which I'm not going to dwell on these equations, but the idea is that you approximate your radiation field everywhere by an ellipse. So the angular distribution is an ellipsoid, and the only free parameter is the energy in this ellipsoid and the direction of the ellipsoid. So you have basically enough information using the energy and the flux to completely determine the ellipsoid direction, and that gives you the closure. And then you have P, the Eddington tensor, and you can solve this equation. It's closed. So M1 is great because it's also purely a hyperbolic system, so it's like a fluid. It behaves exactly like a fluid, so it's simple. We know how to deal with that kind of equation. But there are some catastrophic failure for M1, especially if you have two beams colliding. M1 misbehaves dramatically. So be careful. Be careful. But in this context, we'll show you an example in a minute. It performs really well. It's very cheap. It's as cheap as an hydrosolver. There are a few little details, like the speed of light, for example, that you need to deal with. But I'm not going to spend too much time on that. So this M1 method is basically used by many different codes. And there is one code that is used here quite a lot, which is AREPO, and with the Teyssier simulation. And the Teyssier simulation is based on exactly this kind of system of equations. Okay, so that's an example of such a cosmic ionization simulation. So you see on the right, the red regions are ionized regions. And then you see the transition from ionized to neutral in these fronts. And you see that the topology of this front is very complex. Of course, in blue, it's neutral. And so these are very large box simulations. This box size is several hundreds of megaparsec, really large box. Meaning that galaxies here are very poorly resolved. They are basically resolved by a few resolution elements. So resolution is really bad, meaning that we can't really describe the physics of ionizing photon escaping the galaxy and leaving the galaxy into the IGM to ionize it. So we need actually a parameter, which is the escape fraction. So we need to assign to each galaxy a fraction of the ionizing photon emitted by the young stars, which are, by the way, formed by the gravoturbulent model that I described earlier. So that's a free parameter. That's an additional, free parameter that we adjust. So we adjust this parameter so that we reproduce these results. Right? And so obviously, if you fix your star formation model, so especially if you use the gravoturbulent model where there is no free parameter, at least theoretically, then you have no button you can turn, no knob you can turn, except the escape fraction to reproduce these constraints, right? So that's what we do. We turn the escape fraction up and down until it works. And I'm with you when you think that it's not very satisfactory because, of course, you can get whatever you want. So the next actually step is to try to resolve the ISM. And so that's the simulation that we're trying to do now. So that's a zoom-in simulation of a single, very high redshift cosmic dawn galaxy. It's a dwarf galaxy. So what you're looking at here is the gas density. So very dense blue clumps here embedded in a diffuse medium. That's the H2 fraction. So ionized is white and neutral is black, right? And then that's the same at another epoch. Right? And so you see that the medium is very clumpy. So the resolution here is a few, tens of parsec. So kind of close to the ISM box I showed you earlier. We use the same gravoturbulent star formation model, but now we don't have to assume the escape fraction. We compute it. The escape fraction is an emerging property of the simulation because we have now the resolution to resolve the galaxy. So that's the galaxy, the entire galaxy. But we resolve the holes and the clumps inside this galaxy. And so we can hope to describe how the ionizing radiation is either trapped inside those neutral clouds or is managing to escape outside the galaxy. And so if you plot here on the top plot the escape fraction that we measure around this galaxy at any given time, that's the black line. And in blue, we plot the star formation that we obtain using the graviturbulent model. And you see that they are really correlated in time. But there is a little shift, and that's the shift which is very interesting. So you see in blue, there is a star formation burst here. So after 10 million years, which is really the size of this burst, supernovae kick in, they dump energy and momentum, and then they blow the gas away. So the gas is totally destroyed in these gigantic explosions here. And they literally carve holes in the galaxy, and they expose the young stars, the one that didn't explode in supernovae, and the UV radiation leaks out. That's why the escape fraction in black is actually shifted a little bit, and the escape fraction is very large right after the gas has been cleared out and the hole has been carved. But then, of course, all those young stars, they die out, they disappear, and so there is no more ionizing radiation. And so the gas kind of falls back onto the galaxy and creates another burst where the entire cycle repeats with first a starburst, then large escape fraction, and so on and so forth. So you have this cycle of starburst, then 100% escape fraction, then basically 0% escape fraction, another starburst, 10 million years later, 100% escape fraction, and so on and so forth. So the average escape fraction, which is the dashed line here, so it's a kind of a running average, is around 10%, right? So that's a prediction. That's our average escape fraction, 10%. But it doesn't make sense here because it's never 10%. It's either 100% or 0%. And it's on and off with a duty cycle, which is typically regulated by accretion of fresh gas and supernova explosions. So it's a very subtle picture, which is much more than just one parameter, the escape fraction. Right? And so you also see that the star formation in blue is very bursty, very intermittent, which is a key aspect of galaxies at cosmic dawn. All right. So then that was one galaxy, a single galaxy. Then we moved to the very ambitious project of modeling the same kind of resolved ISM. And when I say resolved, c'est quote unquote, because 10 parsec, my ISM colleagues would say that's not resolved, right? But at least your galaxy is divided up into clumps, right? And holes and clumps. And so we have those galaxies here, which are kind of resolved into clumps, but at the same time, we have a large cosmological box. And by large cosmological box, I mean 1 megaparsec, right? Which is tiny. It's a tiny cosmological box, but that's the best we can do, right? So we try the best we can to either resolve the ISM here and have many galaxies so that we can do the ionization of the universe in this galaxy. And so we can predict different galaxy properties. So we have small galaxies, we have large galaxies, and they have different properties that we want to compare to James Webb, which is what James Webb is observing now, these galaxies. Okay, so we have many results in this simulation, which are interesting, and we can compare to actual observations, including James Webb observations. So the basic quantity we measure is the amount of star we form inside each halo. So these are dark matter halos. The mass of the halo, so 10 to the 10 is a small mass halo. The Milky Way is 10 to the 12, so the Milky Way will be out there. Right? And that's the stellar mass we have in our halo, and the dashes are what is expected from previous work. And so we compare two models here. One model in green, where we have 10 to the 51 erg of energy per supernovae, like I said, right? And you see that it doesn't work. We form too much stars. There's too many stars in those galaxies by at least a factor of several, okay? So that was a bummer, right? Clearly, and we use the star formation, the graviturbulent star formation model. So in our spirit, we cannot touch to that, right? That's the predictive part. But now, okay, supernovae with 10 to the 51 erg per supernovae, obviously that's not enough. So what we did, and I'm a bit ashamed of revealing this here, but it's in the paper anyway. We do something which is to recalibrate supernova feedback, and we assume that it's not 1 times 10 to the 51 erg, but it's 4 times 2 to the 51 erg. And why 4? Because 4 works, right? And so if you use 4, then you get the blue line, which is exactly what we want in terms of how many stars we form per dark matter halo. And if you use less than 4, then it's not enough. And if you use more than 4, then it's too much, right? So that's how I justify this value of 4, because that's the one that works. So that's what we called. So we are back to what we are trying to avoid at the beginning. We are back to calibrating, except this time we use the supernovae energy. So you have another quantity, which is actually the quantity of interest for James Webb, which is the luminosity function of the galaxies. So that's basically how many galaxies you have per co-moving volume per magnitude as a function of the magnitude. And you see that the calibrated model compared to actual observations, pre-James Webb observations, work fine, while the other model, the green model, the galaxies are way too bright and massive. So, okay, that's the first annoying thing. There is a second annoying thing, which is now when we want to compare to the reionization history. So this is the H1 fraction here. You recognize the same curve as before. And now I want to compare two models. One model where we consider that our stars that we form are all single stars. And then we use stellar evolution model that compute how much ionizing radiation are coming out of the stars using a single star population model. And then we get the red curve, meaning that reionization is too slow. We reionize our universe too late. And then we use another model, which is a binary star model, where the UV luminosity output is much higher and also much later. I'm going to come back to this in a minute. If we use this other model, then suddenly the universe is ionized as it should be, roughly, meaning that if you change the stellar population model, you change the reionization history of your universe. So that's the last plot here on the right, which plots the luminosity in terms of photon per second per solar mass in ionizing photon as a function of a stellar population age. And so the single star gives you the red curve here, and the binary star gives you the blue curve. And you see that there is actually late emission of UV radiation in this second model. And that's crucial. Why is it crucial? Let me go back a few slides. Because of this. So when you have star formation, the gas cloud is very dense, opaque, radiation is trapped, escape fraction 0. But then supernovae explode. They carve holes in the ISM, they basically get rid of the gas. But the problem is that supernovae explode means that the ionizing stars are dying. And so when the supernovae are finished exploding, there is no more UV emitting stars. And so you have very little radiation coming out because all the massive stars are gone, they are exploded. But with the binary model, you can delay the UV emitting, ionizing emitting fraction of the stellar population so that you can take advantage of this gas being cleared out, and you can emit a lot of UV photon and ionize the universe more efficiently. So this very subtle difference in the time evolution of the luminosity of UV ionizing photon between the red and the blue model makes a huge difference in the ionization history of the universe, because you have late emitters that can take advantage of this carved hole in the ISM. Okay, so now we can also predict the escape fraction of those galaxies. So that's kind of exactly what James Webb is computing right now. So that's a weird distribution, because you see that most of the galaxies have 0 escape fraction. They are embedded in the star formation is embedded in the clouds, and very little UV radiation makes out. Then you have a peak at 100%. Those are the galaxies which are totally exposed to the IGM, where UV radiation are leaking out of the IGM and reionizing the universe. And then you have a relatively flat power law distribution between the two. But this distribution is just galaxy transiting from 100% to 0% back and forth with this duty cycle that I described earlier. And so James Webb is computing this distribution and is confirming this exactly in very recent paper, that this picture is at least qualitatively correct. All right. So, okay, let me now discuss the last part of the talk, which is this James Webb kind of discovery of bright galaxies. So that's one of the main weird result of James Webb, which is that there is an overabundance. There is too many bright galaxies at high redshift. So let me guide you through this plot. So this is again the same luminosity function, the number of galaxies per co-moving volume per magnitude, as a function of the magnitude. And all the points here are observations at redshift 10. So this is redshift 10, right? Of James Webb. And those are mostly confirmed galaxies at redshift 10. So now we don't have any weird photometric redshift that kind of fool us about those galaxies being really high redshift galaxies. Those galaxies are all real galaxies, spectroscopically confirmed. So, okay, that's what James Webb finds. So what's wrong with these measurements? Well, that's very surprising. So the blue lines that you see in the back here are the mass function, so the number of dark matter halos per megaparsec cube, assuming that the star formation rate here, which is this quantity here, is proportional to the accretion rate of gas into those halos, multiplied by epsilon star, which is this integrated efficiency parameter, which is very hard to make it larger than 100%. Right? So 100% of the baryon of the gas that comes into the halo converted into stars instantaneously, you cannot do more than that. It's not possible. Right? And the problem is that some of those galaxies, okay, these are upper limits, but this one is not, points to some of those, measurements, points to very high efficiency, 30%, at least 10%. Maybe those galaxies are more normal galaxies, more like low redshift type galaxies where the efficiency is more a few percent. And so if you find galaxies which are actually in this range, which we don't at redshift 10, but we might do at higher redshift, then those are called impossible galaxies. They cannot exist, right? Because the dark matter halo that we believe we know the distribution of, combined with 100% efficiency, is the maximum we can do. And so those James Webb galaxies seems to be forming at the maximum efficiency, which is completely not in agreement with low redshift measurements, as well as what we believe the physics of galaxy formation is. So can we explain this? There is two theories, ongoing theories. One, which is the one I explained now, and then the second I will explain later. So the first one is this idea that if your galaxies are sufficiently massive and sufficiently dense, then feedback fails. Supernovae feedback fails, doesn't work anymore. And so you cannot regulate star formation. And then you start to form stars catastrophically, way too efficiently. So that's the model proposed by Avishai Dekol. And indeed, the argument is that if you plot the halo mass as a function of redshift, so the colors give you the cosmological distribution we expect for dark matter halos, you see that if you move in that direction, the expected gas surface density becomes larger and larger. And then the idea is that if you get above this threshold of 10 to the 4, the magic number of 10 to the 4, then supernovae feedback doesn't work anymore. And the belief here is that in this corner of the galaxy population, supernovae feedback fails. So we did simulation of that. So we used a cosmological model here. So that's a simulation of such a galaxy at redshift 10. That's the galaxy. That's how it looks like. It's a big mess. We do resolve the ISM like clumps, a little bit like for the Sphinx simulation. But we have different supernovae feedback calibration, like I explained. We have weak, strong, and fiducial feedback. And so we can't really predict the exact strength of feedback. But to, that's the galaxy, how it looks like. It's like a giant disk. With a lot of star-forming clumps and a lot of feedback. So feedback is really strikingly spectacular, but it's inefficient, indeed, at regulating star formation. And the final result of the simulation is that depending on the strong feedback gives us 10% efficiency, which is really high, and weak feedback gives us 30% efficiency. So it looks like, given the range of uncertainty in our model, especially related to supernovae feedback, we kind of reproduce for this halo mass at this redshift, the idea that the efficiency is very high, like much higher, 10 times larger than low redshift galaxies, all the way up to 30%. So that seems to be a viable mechanism with a lot of course, caveats, especially the fact that we don't really understand how to calibrate our feedback model. Okay, so now the second, let me skip that, I'm running out of time. The second model, the second theory to explain this excess of bright galaxy at cosmic dawn is to invoke the burstiness of the star formation, right? I told you that star formation is very bursty. And indeed, if you take, I will show you some example in a minute. If you take a small mass galaxy, which has an average star formation rate which is very low, but you turn it into bursty galaxy where there's a very high star formation rate and then nothing, then very high, you bias your number counts high. And so you take a lot of small mass, very dim galaxies, and you move them to the right artificially because they're bursty. And so this bias, so if you have more low mass galaxies than large mass galaxies, which we have, then you can boost the number count of large mass galaxies artificially. It's called Eddington bias because they are more luminous in some fraction of the time. So that's the theory that was proposed by many people. And indeed, if you take the bursty star formation rate, you get the red curve here. And then if you smooth the star formation history artificially, then boom, you move everything to the left so that you get rid of the excess of bright galaxy by smoothing the SFR. And so if you look in particular to this example, which is particularly spectacular. So this is a redshift 16, James Webb. So you have 1 point, maybe a second one. And the excess due to burstiness is huge, right? So you can really boost the number counts by the burstiness significantly. The problem, and that's kind of almost the end of my talk, the problem is that can we predict the burstiness of these? So yes, we can. I mean, we can just measure our star formation histories, right? And so let me go back one slide to show you an example. So that's an example of a star formation history of this simulation, this simulated halo I just showed you. So that's the star formation rate as a function of time. And you see there is an exponential growth. So if you detrend the exponential growth, you get this flat residual, which is very bursty. And you see that the typical time scale here are between 1 and 10 megayear, and they're related to the dynamics of the ISM. And you have this typical power spectrum. So that's the time scale or the frequency, the typical power spectrum in this burstiness of the star formation rate. And so, of course, the simulation predicts this burstiness. It's basically a consequence of the feedback model we adopt. And you can see here the Sphinx simulation. So this is the Sphinx simulation in a dotted line here. And that's another simulation, the fire simulation, which is this dashed line. And you see that they agree for very massive galaxies, which are much less bursty. But for intermediate mass galaxies, they disagree. There is almost half a Dex difference in this. And so Sphinx cannot explain the excess of galaxy at high redshift due to burstiness. It's only explained via higher efficiency. But fire explains this excess of galaxy using their increased burstiness. So who's right, who's wrong? Well, we don't know. And so that's going to be my last slide here, which is maybe there is an answer by looking at the clustering of those galaxies. So why is the clustering of those galaxies interesting? Because you can relate how those galaxies cluster. So basically, are they close to each other or are they like randomly distributed? And this is encoded by the bias. And so why is it a way to disentangle? Because the clustering of a galaxy population is related to the halo mass in which they are. So let me go back. You see that here. Okay, let's go back a lot. So here we have a certain stellar mass here as a function of the halo mass, right? And so here we have very massive galaxies in terms of stellar mass, and here less massive galaxies in terms of stellar mass, but they are in the same halo mass. And so the clustering, the way those galaxies cluster, depends only on the halo mass, right? So that's the way to measure the typical halo mass in which they are. That's what the clustering tells you. So this clustering analysis has been performed by those people here. And those are the data points that you see here up to very high redshift. So that's redshift 10 here, 12. And then they compare to two theoretical models, which are the one we discussed today. This one, which assumes that the star formation rate is not bursty, but the efficiency is very high. So basically the bias is larger because you believe that those galaxies come from large mass halos that are not bursty. No Eddington bias. They are just intrinsically brighter. And then the other model, which is those 2 points here, that assumes that the galaxies are bursty. So they come from smaller mass halos, which are less biased, but are promoted via the Eddington bias because of the burstiness. And so you clearly see that one model predicts a low bias and another model predicts a high bias. So now those are the observations. I'll let you judge, because it's very, difficult measurements to do and very controversial. But that might be the way to disentangle the two models to pick up the population that has the right clustering. Might be the answer to this. So that's my conclusion here. So we're trying to do some predictive simulations using star formation recipes which are based on turbulence. Of course, I told you that in terms of supernovae feedback, we have to adjust the supernovae energy in order to really be able to reproduce the result, which is kind of not very satisfactory. The high redshift galaxies have a very high efficiency, higher than 10%, no matter what feedback we use. And we believe this is due to the fact that the density of the gas is very high and the turbulence is very high. And the two combined gives you an efficiency of 10% and maybe 30% for as high as 30% for very weak supernovae models. So that's why our prediction is not very accurate, right? The star formation history is indeed very bursty, but the level of variability is crucial, is a crucial quantity you need to compute properly in order to estimate the Eddington bias that you will get in your galaxy luminosity function. And so we don't know, but maybe the clustering analysis will kind of solve the question by picking up the right halo mass for those galaxies and therefore tell us which of the two models is correct. I'm done.
Well, I'll speak loudly. Thank you very much, Romain, for this really great picture. Gives us a feeling to what might be going on, I guess, and the questions are still open. And I see there are already some hands up. If I could take questions first from students. Yep, on the top right. I don't know whether the mic is working, but we'll try it.
Thank you for the wonderful talk. So in your models, one thing you consider is like the supernovae feedback, but I remember that at some point of time you have this a lot of AGN activity as well. I do not know if it is relevant at this redshift, but if it is, because I remember there's something around 6 that James Webb discovers, but this is like much higher redshift than that. But like, if there is AGN feedback, I would expect turbulence and this luminosity, all of that to be affected. Is there anything? And if so, can you include that?
Okay, so indeed, so I haven't discussed, neither included in the simulation I presented AGN feedback. But you're right, AGN are really a very important aspect of all this for multiple reasons. One reason, you're right, is that they contribute to the luminosity. And so it's really the game of the observers to try to disentangle using various spectral signatures, whether they do have an AGN that contributes to the luminosity of the galaxy or not. And some of the James Webb galaxies shows that they do have an AGN. Now there is another issue, which is once you know you have an AGN, can you measure the black hole mass? And that's much less solid, because usually you have to use spectral properties that are usually calibrated at low redshift. So we are not the only one to calibrate stuff. Observers also calibrate stuff. And so they calibrate their relation between the black hole mass and whatever spectral signature they used. And so applying those calibration to high redshift is a bit fishy. So the black hole mass they get from those observations, I'm not gonna, die on the hill of defending the values they find. Now, in terms of the simulation, you're right that AGN, especially AGN feedback, if the black holes are massive enough, AGN feedback could make a difference. So we do actually have simulations, including AGN. I didn't mention them because it's work in progress. And it looks like even if the AGN is big enough to really maximally produce feedback energy, the feedback is not enough to change the picture. So these galaxies are really, really hard to beat in terms of either supernova feedback, really too weak to do anything, and even AGN feedback seems to not doing much. And so, but of course, this is just me, and this is unpublished results. So, but it looks like this is what is emerging. That any kind of feedback, even including AGN feedback, seems to not make a difference in the mass assembly and the star formation rate in those galaxies. But to be confirmed, obviously.
Yes, so first of all, thank you very much for your great talk. So my question is regarding the modeling of star formation at high redshift. How accurately can we actually model with which masses these stars form? Because I was thinking about population pre-stars, which probably have a very, very different initial mass function than stars forming today. And so this population would have a very different output of ionizing radiation, right?
Yes, totally. So there are multiple aspects here, but so pop-free stars, we don't model them. We assume that they formed earlier, like really at the very end of the dark ages. And then they form like everywhere in small mini halos. Then they all died, enriched the universe, and that's it. They disappear from the picture. That's a simplification, of course. And so then we start after that. So our simulations start after that. So once the universe is kind of pre-enriched at a very small level, let's say 10⁻³ solar, and then we form our stars in atomic cooling halo, mini halos, but atomic cooling halos in a more traditional way. Even though the ISM is very weird and different, but we still form stars. We call them population 2 stars, right? And so you're totally right that the IMF is completely an open question, especially for James Webb. Playing with the IMF is really what people are doing. So we used an IMF, which is the Chabrier IMF. And, but you can also blame the stellar evolution models. The stellar evolution model, as I showed you, right? If you change from a traditional single star model to a binary model, you get totally different radiation output, especially the timing is very different. And for us, the timing is crucial. And so you can also come, and the model we use, by the way, for those experts is called BPAS. It's a binary stellar evolution model that has been produced 10 years ago, probably. Now there are more, modern stellar evolution model that produce different output of radiation at different energies, and is clearly crucial. Yeah. So totally, that's interesting because that's a way, maybe not very clean, but that's a way to put constraints on those stellar evolution model, because we need those UV radiations to complete the ionization by redshift 6.
Okay. I'd like to make the questions open to everybody. So please ask another question. I see one down on the right. Speak loudly.
Hi, thanks for the talk. So briefly mentioned about the M1 closure relation that you use and the problem reversing. But can you highlight a bit, like in large cosmological boxes, like unless you're resolving the stars, how important beam crossing would be? And on the similar note, like do we always expect the escape fraction around a halo to be isotropic?
Can you repeat the last one?
Do we always expect the escape fraction around the halo to be isotropic? Like, can you have scenarios where the escape fraction around, depending on the orientation of the cosmic web, is like not non-isotropic? So like one side of the halo, you have a large ionizing photons, and then one side you do not have.
Okay, so M1, so I mean that's this image gives you a typical, and actually there is a similar image in this building over there from the Teyssier simulation, and this image gives you the typical shape of the ionizing fronts, and if you use different codes like C2 or whatever ray tracing codes, which are totally not M1, which have their own issues. For example, they scale very badly with number of sources and whatever. But they still find very similar morphologies, at least at the level of precision we are, right? For if you want to fit those data, right? So the M1 in this case is okay because we don't really suffer from the beam collision infamous test where M1 fails miserably. We don't really have that, right? But now at smaller scale, so if you now focus on those simulations, then you can see some much weirder results. You know, obviously in this case, you either accept the weird kind of results you get, and that's what I do. I made peace with that, or you try to develop better models, right? And so now people are working on the model called M2, which might be the solution to all our problems. I don't know. The second question was the escape fraction. So I'm not sure I understood everything, but so maybe I can show you this plot that I haven't shown. So in the escape fraction is a function of time for each halo. It's basically oscillating between 100% and 0% on and off like that. So you can compute the mean escape fraction for a given halo, right? I'm not sure it makes much sense, but you can, right? And then you can also compute the mean escape fraction per halo masses. So you basically bin your halo population in different masses. And there you see it's again very bursty. It's less bursty for larger halos. So it's not, for larger halos, it's not 100%, 0%. It's more like, you know, smaller values. Even the instantaneous values is not 100% or 0% anymore because you have more star formation sites, they're bigger. But also you have a very clear trend that the escape fraction is smaller for larger mass halos. Right? And so that's interesting because if you convolve your halo mass function, your halo distribution function, with the escape fraction, which is roughly 10% at the small halo mass, and then it drops for large halo mass, then you have converged results that the halo population you really need to understand for ionization is basically those guys here at 10 to the 10 solar mass. And that's the population you want to get correctly in order to describe the ionization, because the big guys, even though they are, you know, not negligible, but the escape fraction drops. And the little guys, you have many of them, escape fraction is large, but they are less luminous. So it's really the intermediate one that contribute most to ionization in this model, right? Of course, you can argue that AGN are missing from this picture, and maybe our escape fraction is wrong, right? So there's a lot of caveats, but you know, with the escape fraction as a function of halo mass, you can really identify what halo mass is the main contributor to ionization. I don't know if it answers your question.
Okay. For the moment, I don't see any more questions in the hall, and I don't see any questions online. So I'd just like to make an announcement before we thank Romain. First of all, there will be student meeting where students can meet Romain over some beverage in the beer garden on the Neckar. And this is organized by Vincent Bronner. So if you want to stack yacht, so please go to Vincent if you want to join in on that. Secondly, everybody's invited to dinner at Dorfschenker, Neunhelmer Marktplatz, starting at 7 p.m. So look forward to seeing you there. So now it just remains for us to thank Romain for this extremely informative and incisive view of what might be going on in the very high redshift universe right now. Thank you very much, Romain.